Hello friends, welcome to the Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created a bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, stacks, queues, and linked lists. Also, I have uploaded the code for this problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Lowest common ancestor of a binary tree, number 4. So it looks like there are three more problems in the similar lines, basically on the lowest common ancestor of the binary tree. But this is a fourth, another variation, it seems. So let's go ahead and look at this problem. Given a root of the binary tree and an array of tree node objects, nodes, return the lowest common ancestor, LCA, of all the nodes in the nodes. Right, so we are given with a binary tree and a set of tree node objects. So now our task is to find the lowest common ancestor of all these nodes. So previously the problems were like you are given with two different nodes and you are asked to find what is the lowest common ancestor of the two nodes. But in this case, the nodes are not necessarily be 2, but it could be any number, maybe 10, 5, anything like that, right? All the nodes will exist in the tree. Let's continue that problem, right? All the nodes will exist in the tree and all values of the tree's node are unique. So that's an important information. So basically all the values in the tree are unique. And obviously the given nodes should exist in the tree, right? So that's another thing. So that's what the problem statement is. So the lowest common ancestor we need to find for all the nodes, not necessarily just two nodes, right? Let's go look at one of the examples, right? So here in this particular case, the nodes given are 4 and 7. So this will be coming back to like only two nodes are given. And what is the common ancestor of these two nodes? Right? So 4 and 7, if you look at this picture, right, the binary tree, 4 and 7 are right here and the lowest common ancestor will be 2. So this will be like the most common problem. But here, since we were given with an array of objects, right, so it's not necessarily 2. So let's go ahead and look at another example where we can find more than 2, right? So here in this example, right, example 3, we have like four different things: 7, 6, 2, and 4, right? So 7 is right here, 6 is right here. If you consider 7 and 6, what is the common ancestor? 5, right? And if you consider, if you add 2, yeah, so 6, 7, and 2, still 5 is the common ancestor. And 4, 6, 7, 2, 4, what is the common ancestor? 5, right? So that will be the lowest common ancestor, right? So that's how we will have to essentially find it out, right? So that's a problem statement. Let's look at like couple of approaches here in order to solve this particular problem, right? So let's say I'm calling this as approach 1 to start with, right? So in the first approach, what we're going to do is essentially for each of the nodes in the nodes array, right? Each of the nodes in the nodes array, we will find the path from root to the node, right? That's the first thing. So what does it mean? So for example, if you look at the example 1, right, in this case, so we are given with 4 and 7. So what is the path till 4? 3, 5, 2, 4. That's what I have here, right? 3, 5, 2, 4. And what is the path till 7? 3, 5, 2, 7, right? So 3, 5, 2, 7, right? That's what it is. So that's the first step, right? Find the paths from root to each node in the nodes array. Nodes array is like 4 and 7, right? So we found the path. Now, in the second step, in the paths, look for the non-common node in the path, right? So what is a non-common node, right? That node before the non-common node is the answer, right? So basically, if you look at the index 0, 3, 3, so it matches. So that could be the common ancestor, but let's go and look further. 5 and 5. So we can say, okay, 3 is not the common ancestor because we have a new common ancestor, right? So go further. 5 could be a common ancestor, but go further. 2 and 2. So 2 and 2 is again since they are same, that could be a common ancestor, right? And 7 and 4, this is where the elements are differing. That means 2 must be the common ancestor, right? So at index 0, 1, 2, right? That is the node which is the answer, right? So this is how the approach 1 would work. Essentially what we are saying is, for each node in the nodes array, right? We go find out the path, right? And from all these paths, check where the non-common node exists. The common. So 3 is common in both. 5 is common in both. 2 is common in both. 4 and 7. These are not common. So what is the last common node? This one, 2. So 2 will be the ancestor. Basically the lowest common ancestor, right? That's how we are going to proceed. So let's go ahead and look at the time complexity for this, right? So in order to get the path for the node, right? So per node, each node, right? Let's say a binary tree has n nodes, right? And nodes array has m nodes, right? These are just taking an example, right? So binary tree has m nodes and node has n nodes, right? So in that particular case, we will say for each node, right? In order to get the path, we will have to possibly traverse through n nodes, right? So that means m into n will be time complexity for just getting the path, right? And once you get the path, you need to go through these individual paths in order to find out what is the common ancestor, right? So that would be how many, because basically when we say there are n nodes in the binary tree, typically the depth would be log n to n, anywhere from log n to n, right? So if you say log n to n, anywhere. If it is a skewed tree, right? So then we would say, okay, there are n nodes, and n is the depth. But if it is not a skewed tree, if it is a perfectly balanced tree, we will say log n. So in the worst case, we will say, okay, n nodes are there, right? So the total complexity would be order of m into n plus n. So that would be, we will say m into n, right? So that will be the total complexity, right? And total space complexity for each of the paths, right? For each of the paths, we are using log n, let's say. But in the worst case, n. So for m, we are using n. That is the space complexity. So we have time complexity of order of m into n and space complexity also order of m into n in the worst case when you go with this approach number 1. So before going to the implementation and all, let's go and look at another approach where we will be using a DFS, right? So I have an approach 2 here. We'll see the DFS. So in the DFS, as the name stands, depth first search, at every step we will be counting the number of nodes found, right? At whatever the stage that you are in, you just find how many number of nodes you already found from the nodes array, right? From the nodes array, let's say if there are m nodes, as we said, right? Out of m, how many you found, right? At which point you are able to find all the m nodes, right? So that is where you will assume, okay, from here on, I found all m nodes during my depth first search. If you go back and look at depth first search, right? So while you are at 3, you will be exploring one of the paths, right? 5. And at 5, you'll be exploring one of the paths, 6. So once you explore 6, this path, 3, 5, 6, were you able to find all the m nodes is the question. No, in this particular case. And then go back. 5, 2, were you able to find all the m nodes? No. And 7, were you able to find all the m nodes? No. But you are able to find one node, right? But now, till we are able to find all the m nodes, we will be going down to the paths. So that's how depth first search we are going to look at, right? And as long as we find all the m nodes, that is when we can say, okay, we found all the m nodes starting from node X. So anywhere from that, it could be the LCA in that path. So now we have to track the LCA. So whenever we are good to track the LCA, that is when we will say, okay, this particular node is LCA, right? The least lowest common ancestor. So one of the caution that I would like to mention here is, once the LCA is assigned, it should not be changed. So we have to be like cautious about coding this particular thing, right? So let's go ahead and understand what that it means, right? So for example, 4 and 7, right? So when we are here, we go depth first search into this, we are not able to find any of them. But after 4, we are able to find all the nodes in the nodes array, right? So after 7 and 4, we are able to find. So at here, at 2, we will say, okay, we found all the nodes in the nodes array. So at 2, we will assign LCA. But when you return back to 5, we will still say, okay, I found all the nodes. But at that point in time, you have to see whether your LCA is already assigned or not. If it is not assigned, then only you assign. Otherwise, don't assign. So when we go look at the code, right, it will be a bit more clear about what I'm really talking. So that is for the explanation is concerned. So we looked at two approaches. So the code that I'm going to show you is for the approach 2. So approach 1 is pretty much simple. Basically, what you're doing in approach 1 is take all the paths and go through all the paths that you discovered so far, right? So that has like too much complexity in terms of the space and time, right? But in the approach 2, we are going to look at the complexity later once we look at the code. So let's go look at the code for approach number 2, right? So initially we are given with this lowest common ancestor, and the input is root and the nodes array. This is what will have all the nodes within the binary tree, right? So to start with, what I'm going to do is I'll put all of these into the hash set, right? All the nodes into the hash set. So these are the nodes that we are going to find. As and when we find, we will be saying, okay, this node is existing, right? So total number of nodes that we need to find is nodes.length. That's what I'm initializing. And I have another variable to keep track how many nodes we are already found to 0. And I also initialized LCA to null, right? Because to start with, they are null. And after that, we are going through our DFS search. So what DFS will be passed with? Root node and the hash set, right? So all the magic happens within the DFS. Okay, let's go look at that. So if the root itself is null, right, we are going to return 0. So what is this 0 here signifies? It is talking, or it is telling us, saying, okay, I found X number of nodes in my right subtree. I found Y number of nodes in my left subtree. So that is what it is saying. Okay, and so current. If the current node is one of the nodes to be found, then initialize current to 1. Otherwise, initialize to 0. So this is important here. So if current node is one of the nodes to be found, then you initialize it with 1. Otherwise, initialize it with 0. And after that, you go and find how many of them in the to find are there in the left subtree, and how many of them of to find are there in the right subtree, right? So basically, we are trying to find how many nodes are there onto the left side, how many nodes are there onto the right side, right? So once we have those counts, this is where we need to pay the attention, right? So if left is greater than 0, or right is greater than 0, or current is greater than 0, that means if you are managing to find any of them, right, that is when we are going to check if left plus right is equal to total, or current plus left plus right is equal to total. That means, did we find the total number of nodes or not? Simply, right? So just check here. Let me write a comment here. Check if all nodes are found or not, right? So if all nodes are found, then only we will be entering this if, right? If some of the nodes are not found, then we don't have to enter in this. But if all nodes are found, then we will enter. And that is when you check if LCA is still null. That means if LCA is not assigned, right? So remember, for 7 and 4, at 2 we will assign LCA, but at 5 also we will still have the found value to be 2. At 3 also found value will be 2, because under the left subtree all the 2 are found. For 5 all these 2 nodes were found in the right subtree. That's the reason why we check if LCA is equal to null or not. We assign LCA only once. So if it is assigned, if it is not assigned, not yet assigned, then you assign the current, whatever the node that you have, right? But this one, you only do this only when all the nodes are found. So one more thing that we can add instead of doing here, right? So we can combine these two if statements. If LCA is equal to null right here and LCA is equal to null, right? So that we don't have to come even in this part. So we can probably combine those two if statements. That's an optimization that we can think of. So, and if it is not, finally what we are going to return for this particular subtree? Current plus left plus right. So how many ever nodes that you found in the current or left or right, right? That is what you are going to return to the recursive DFS, right? So this is how the recursion will work with the DFS. So at the end of it, LCA will be loaded with the node which will be the lowest common ancestor of all the nodes that are given in the nodes array, right? So that's how it is going to work. Now let's go ahead and look at the time and space complexity, right? So here, let's take those assumptions. Basically, the binary tree has n nodes, and nodes array has m nodes, right? So here, our DFS, since it is a DFS that we are coming from the root, right? How many times we are going to go through the entire tree? It's one time, right? How many nodes are there in the binary tree? N nodes, right? Irrespective of m. So we actually don't need this m here, right? We actually don't need this m here. It doesn't matter. The m could be equal to n also. But how many times we are going to traverse through this? Once. That means order of n, right? Plus, is there any complexity that we need to add? Not really, right? So as long as you have n nodes, right? You traverse through them and find out how many nodes you are finding. So the total complexity would be order of n, right? Time complexity. So this will be time. Okay. Next, go to the space. What space we are using here? So we are using a found variable and a total variable and a tree node variable. So since these are three variables, we don't have to really worry about anything else. Now, is there any other space that we are using? Yes, we are using this hash set. But hash set, how much space that we are using here? As we said, the length of the nodes is m, right? So the space complexity will be order of m. So that's how it works for time complexity and space complexity. And one more thing that we are not considering here. So since we have implemented a recursive DFS, right? So there is a space complexity, although it is not we are explicitly using, but there is an implicit stack space that will be used as part of the uh, recursion. So that space we have not considered here. But if you add that space, right, order of m plus order of n in the worst case, right? So if the tree is skewed, like left skewed or right skewed, all the nodes are like in a skewed binary tree, then we will say space complexity will be order of n. So given that, the total complexity would be order of m plus n. So time will be order of n and space will be order of m plus n. Hope that clarified all the questions. If you have any further questions, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted this code to the GitHub repository. You can find the link in the description below this video. If you haven't subscribed to the channel, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will get notified about all my future videos. Thank you for watching. I will be back with another video very soon. Till then, stay safe and goodbye.